welcome to another session. In this session, we'll see some important aspects of Mosfet. In this session, we'll see about the different operating regions of the Mosfet, the conditions to keep the Mosfet in the different operating regions, and we'll also have a quick look at the IV characteristics of the Mosfet. Let VGS be greater than VT. Due to this, a channel is formed. Now apply a small VDS. The carriers or the electrons in the channel start moving towards the drain. The MOSFET is said to operate in the linear region now. It's because the current IDS has a linear increase with voltage. It is also called the ohmic region. The relationship between the current and the voltage in the linear region is same as that of a linear resistor. That's why we call this as the ohmic region. So, what should be the different voltages to keep the MOSFET in the linear region? The first condition should be VDS is small. VDS should be smaller than VGS minus VT. Rearranging the equation, we get VDG should be less than minus VT, which yields VGD should be greater than VT. VDS should be small to keep the MOSFET in the linear region. But if it is too small, it will turn off the MOSFET. So VDS should be greater than 0. We can split VDS as VDG plus VGS. VDG can be rewritten as minus VGD. So VGS minus VGD should be greater than 0, which yields VGS should be greater than VGD. So the two essential conditions for the MOSFET to be in the linear region are VGD should be greater than VT and VGS should be greater than VGD. As VDS is increased, the channel starts to constrict near the drain end. The channel region has been shown separately now. The channel constricts, and if you still continue to increase your VDS, the channel becomes a point at the drain end, which is called the pinch-off region. The operation in this region is called the saturation region. So beyond the pinch-off point, the current is constant, irrespective of any changes in VDS, or IDS is independent of VDS. Can we say that the current has saturated? That's why this region is called the saturation region. As in the case of linear region, we derive the voltages for operation in the saturation region. Unlike the linear region, for the operation to be in the saturation region, the main condition is VDS should be large. How large should it be? It should be greater than VGS minus VT. So VDS minus VGS should be greater than minus VT, which gives us VDG should be greater than minus VT, or VGD should be less than VT. So far, we have discussed how the drain to source current will change. When it is in the linear region, it will increase with VDS, and when it is in the saturation region, IDS will be constant irrespective of any changes in VDS, and when the operation is in the cutoff region, IDS will be 0. Now, we'll go ahead and derive the IV characteristics equation. So, IDS depends upon charge in the channel and speed of the carriers. First, we'll derive an expression for the speed of the carriers. The carriers move in the channel. They start from the source and they move towards the drain. So the carriers cover a length of capital L, and the lateral electric field VDS is responsible for the movement of these carriers. So the carrier velocity V is mu into E. Mu is the mobility and E is VDS by L. So V becomes mu into VDS by L, which is taken as equation number 6. So the time taken for the carriers to cross the channel whose length is L is T is equal to L by V. We have got the expression for V in equation number 6. Substitute this, we get T is equal to L squared divided by mu into VDS. The channel charge density is equal to the gate capacitance times the gate voltage in excess of the threshold voltage, or VGC minus VT, where VGC is the average gate to channel potential and VT is the threshold voltage. Gate capacitance is epsilon aux WL by T aux. Remember, W is the width of the transistor as was seen in one of the previous slides. Epsilon aux, permittivity of silicon dioxide. T aux is the thickness of gate oxide. Epsilon aux by T aux gives C aux. We have come to the end of this session. In the next session, we'll have a detailed discussion on the different non-idealities of the MOSFET. Thank you.